All right. Hi, everybody. Welcome back to Office Hours. Today is the last Office Hour session of Organic 1 with me. So kind of a nostalgic moment, a full circle moment for a lot of us. So I'm happy that you guys made it to this point, that you guys stuck it out, and hopefully we can, one last time, clarify any last concerns that you have. All right, so let's kind of just start with these predict the product questions. So this kind of encompasses all of exam 4 material. Specifically, we are going to really focus here the chapter 11 stuff, the epoxide stuff that we discussed yesterday, okay? So for A, it looks like the first step is going to be doing some sort of free radical bromination. So we know that brominating like that is going to be regioselective for the more stable position. So I'm thinking that the bromine is going to add here, okay? And then looks like in step 2, that's a bulky base, okay? So that's probably gonna do the elimination step, E2. Okay, so I'm thinking that we're going to get the Hoffman alkene, okay? So it's probably going to be, something that looks like this. So here, that's the product of step 2. And then 3, it looks like we're treating it with that peroxy, reagent that generates an epoxide straight from an alkene. And it's MCPBA dissolved in this, again, an inert solvent. This is DCM, dichloromethane. So from this, alkene starting material, we can draw the epoxide products 2 ways, and I'll show both. So we can either keep, the main molecule planar, okay, like that, and then just show the stereochemistry like that of the epoxides. Okay, so that's one way. Or what we could do is we could actually rotate the starting material 90 degrees, so it looks like this. Okay. And then you can draw the epoxide reagent, MCPBA, approaching from the top or from the bottom. So if it came from the top, it would be like that. And if you drew it from the bottom, it would look like that. Okay, and you keep the stereochemistry the same. And if you were to rotate this one or pancake flip it forward like that, this one turns into that one. So it actually just proves that you get, 2 main enantiomers, okay? So I just want you guys to be able to see that both of these are the same types of molecules, all right? So that's A. Okay, so in B, it looks like we're gonna do Halohydrin conditions. So remember, we go through that halonium bridged, chloronium, bridged intermediate here, and then water is going to attack at the more substituted side. So that would be, this tertiary position over here. So I'm expecting, as a result of step 1, a halohydrin that looks like this. And I'm ignoring the stereochemistry, okay? So it's kind of important to note that the hydroxyl portion, that from the water, is going to add at that more substituted position of the alkane, and that results in the halide being on the less substituted, okay? And then step 2, it's just one of those alkoxide anion synthesis reactions. So remember, 2 equivalents of pure sodium or lithium metal is effectively going to remove this proton, make it negative, okay? And remember, we said that it's going to do an intramolecular epoxide closing, where this nucleophile is close to that electrophile, or that electrophilic carbon. And what essentially happens is that we kind of had this closing reaction. So as a result, we're going to get this main epoxide. And, in terms of stereochemistry, here is, I guess, one version. And then here's another. Okay, so those are the 2 epoxides from steps 1 and 2. Then in 3, it looks like I'm treating it with ethanol and hydrochloric acid. So this is actually acid catalyzed, epoxide opening. So remember, we said that the role of the catalyst is really just to protonate the oxygen. Okay, so essentially what that would look like is, I'm going to draw it on one of them, but you basically protonate, and we call this, basically, I call it ring activation. I don't know if that's still what we call it in lecture, but this is ring activation. You're basically making this, what did we say last class? We're making the blank more blank with acid conditions. We're making the blank more blank. Exactly, and that's important. So everybody, I know you guys think that's like a weird thing that I'm like, just throwing out there. That's been asked before. So under the acid catalysis ring opening, that acid is functioning to really make this electrophile more electrophilic, and we proved that last class. Okay, so once it's protonated, basically, we have this main ethanol reagent, and we said that that's regioselective for the more substituted, position of the epoxide. So clearly we have, you know, this side or that side. So I'm expecting ethanol to add into this more substituted side. So our two products really, if I just kind of skip those depronation steps and all that jazz, it really turns out to be something like this. So if, notice, if the wedge face is kind of blocked because of this is the stereochemistry, then what you get is this ethanol on the dash, okay? And you have the hydroxyl group over here, okay? But then if you started with the dash one, you get the ethanol coming in on a wedge and then that hydroxyl group on a dash. Remember, it's kind of this anti-addition because of the stereochemistry. So let's kind of just talk about that. That was kind of an anti-addition. And that makes sense. That's just based on sterics. Okay, if there's a wedge here, you know, we're kind of sterically limited to the back face. So that's why the ethanol comes on the back while leaving the hydroxyl group a wedge. And then if you look over here, if we started with this dash starting material, then it can only add from the front face, which is a wedge, and that keeps the hydroxyl on the back. All right, so that's how I would do 2, or I guess 1B. Everybody good on that one? Okay, left. Is it always wedge wedge or dash dash on the epoxide like in B? Do you mean both of the bonds in the epoxide? The carbon oxygen bonds? Yeah, they're both going to be the same, whatever they are, because it's like concerted type of mechanism again. Okay. Yeah. All right. So we're in C. Okay. So again, C is going to be free radical bromination conditions, and again, remember, one of the conditions for that in the mechanism was we're removing a proton, right? So my instinct would be straight, you know, to go straight to this quaternary position. Actually, I just want to modify this because I actually could see how this would get a different product. Let's just make this a propyl group, okay, just for now. And basically, I want to do free radical bromination. And again, we have to have a proton, okay? So at this quaternary position, we really can't remove any protons. We would exceed the octet. So no, we're not going to be able to do it at that position. But the next best one is this tertiary position where we do have a proton here. So that's why I would expect, you know, basically a result of that step would be the bromine here. Okay, and LDA is basically just going to be that bulky base that forms an alkene. So I'm gonna imagine something like this. Okay, so that. And then MCPBA is gonna form the epoxide from that alkene. So that's basically going to do and the way you can draw this is that, and you can also draw the dashed version. That. Okay, so you have these two main diastereomers. Then in step 4, it looks like we're treating it with sodium thionyl. I think that's the name of it. I'm not really sure what the name is, but it's basically basic conditions. It's a nucleophile. So in this situation, we're actually going to attack the less sterically hindered side. So probably these positions on the epoxides. So that's nice. So essentially what we can see is we're going to get a structure that looks like this. So let me just draw the mechanism for you guys. This is a funky problem. So it's going to attack here, form a carbon sulfur bond there, okay? Break this bond, okay? So we generate the O minus. So essentially what you're gonna get is this substituent oh, this is a crazy one with the stereochemistry. Okay. And you're going to get let me just make sure my carbons are good. 1. Oh, my carbon count is too high. So this should actually be
Excuse me, Stephen, could you move your paper just?
oh, yeah, sorry about that. Yeah, there you go.
Yeah.
And then it would be,
thank you.
Yeah, and it would be this. Okay, sorry, that was crazy. Okay, so let's kind of just we'll talk ourselves through this and how I got there. Okay, so basically the chiral center here, I didn't touch at all. Okay, so these centers in there, in terms of their configuration, are going to stay the same. So how did I get, you know, these products? So we know that there's going to be one carbon atom and then the new carbon sulfur bond. Okay, so that's basically one carbon atom and then the new carbon sulfur bond. One carbon atom and the new carbon sulfur bond. Okay, so that's kind of explaining that. The O minus, whatever the, I guess whatever the stereochemistry of the epoxide was, is what the O minus is going to still be. So again, if it was a wedged, you know, epoxide in the beginning, we're gonna have a wedged O minus group. Okay, same thing here. Dash O is gonna be a dash O minus group. And I'm not really indicating it, but notice how there's two bonds to this carbon from the epoxide. There's this dashed bond and then this other bond that I didn't really show any stereochemistry because I didn't want to make it confusing. But essentially, it also would basically be a wedge here, essentially, but I didn't draw that. Okay, so if you get a situation like this, just make sure you kind of follow what the alkoxide is going to be, and then, you know, whatever the other group is obviously has to be from the opposite face. Okay, so that's the dash. Okay, and that's kind of how I got there. And I left it as O minus on purpose because typically with these basic, you know, opening conditions, you have to have another workup step, like a step 5, H2O and HCl, to like protonate that O minus to make it OH. So there are questions on the test that don't have this protonation step, and you have to know to leave it here, okay? That's sometimes a common trick, so just keep that in mind. So if I were to keep it protonated with that protonation step, it would be those two main diastereomers, all right? Any questions? Let me see the chat box. Could you explain why in this example the epoxide has a WD but also a bonded plane? Brian, did I answer your question? Yeah, I figured. Okay. That's it. So anybody have any questions on chapter 11 material? Want me to go through maybe not a couple more problems, anything like that, or no? Okay. I don't really have anything planned for our final review, but okay, Abby question. Why is it in plane? Which one are we talking about? What's in plane? Brian's question. Could you explain why in this example the epoxide has a wedge dash but also a bond in plane? Okay, so what I was saying is back to this, I think we're talking here. This is basically a dash. Like if you were to write it properly, here, let me just draw this again. It properly, it would be wedged. So this funky kind of structure, that. Okay, so just kind of to show the real stereochemistry, but I didn't want to, like, you know, make it confusing. What happens is that SCH3 group in this example has to, you know, approach, it's kind of confusing honestly, but it's this less sterically hindered side. Okay, so if it's going to attach here, that's going to break this bond. Okay, so hopefully you guys see that. So this wedged carbon is still going to stay the wedged carbon, and then you're just adding the S onto that wedge. Okay, I hope that kind of makes some sense. So really from there, what you can imagine is you have this, and then you just have that swiveling effect. So you have that O minus. Do you guys all see that? I think that should. Yeah, I was just making it plainer because that's something, this is very kind of crazy looking. And it's basically equivalent to, like, if you were to rotate this, like, you know, 90 degrees, you would see it flat, I guess. Okay. Okay, so again, like your synthesis are pretty reasonable. That's a great question. On this exam. So I would just go over like the main routes in chapter 6 and 7. Like, you know that we can really only modify it so many ways, like at this point in organic 1. So I would remember how to do that alkene route, you know, the acetylide addition route, halogenating, all those things. We can do a couple examples today. A lot of synthesis practice if you want. Any tips for this exam? I think you just, okay, yeah. So this is what I would recommend. Go to the exam 3 review video on YouTube, the one that we spent an hour on, and I like wrote through all those boxes, like, and I wrote every reaction out. literally, if you don't want to watch any of my videos ever again, that's definitely one to watch because it's going to review all the chapter 6 and 7 reactions. Today, I was planning on doing again that box thing where we were going to just write in the new reactions and make a nice summary sheet. And then I think the most important thing is really just to know all of those details about every single reaction. That will probably take you the farthest. And then if you have extra time, you know, spruce up your knowledge with maybe some chairs and some configuration stuff, but don't try and do every single problem again. Just make sure you can at least do one of each type, basically. So to check yourself, I would just go to the critical thinking questions of, you know, the student workbook and just do at least, you know, 2 from each chapter. You know, that's not a lot. That's probably like a total of 10 questions or something. And then that should be good. Okay, so in the chat box right now, guys, just maybe put the chapter that you think we need the most coverage on for the final. We have 2 hours today, so we have a lot of time. So if you think you could list a chapter, what would you kind of prefer us to do? Or you could kind of say the name, whatever. Okay, 11. The very beginning, okay. I'll just let you guys kind of populate that and then you can kind of do some stuff. Okay. So it seems like really the consensus right now is 2 and chairs and all that jazz. So definitely we'll cover that stuff. It looks like, what else are you guys saying in here? Some saying 6, some saying 2. Well, honestly, most of you guys are saying 2. Wow. Okay, so we can do that. All right, so let's kind of just jump into some stuff. So the first thing we're gonna do again is, so take a sheet of paper, okay, fold it in half, so hot dog style, if you guys have one. Okay, fold it in hamburger style once, and then you're gonna do it one more time. I know, I was saying the same thing. I figured, you know, typically on exam reviews, there's a lot more people. I guess people don't know about it. Oh, well. I also think because your final's not for a little bit, so. All right. Okay, so hopefully everybody has their nice sheets together. Okay, so we're here. And I'm gonna get my notes ready for you guys. Sorry, one sec. I guess I didn't open the right thing. Here we go. Oh wait, so real quick, everybody, I meant to do this at the beginning, but I didn't. I'm gonna put, anybody know how I can upload a document into the chat box? I really wanted to do that. File is, oh, click, oh jeez. Oh, just drag it in, got it, okay, cool. All right, so everybody take this file. Wait, it's not. Guys, I'm sorry. I don't know how to upload this file. Can someone like verbalize it for me? I don't know. Where's the file button?
In the chat, if you like click on the chat, and then it should be in the bottom right. It says file, and then you click your computer.
So weird, I don't see that.
It might be different for the host.
Yeah. Okay. Darn. I thought it was easier to upload in here, but I can't figure it out. All right. Yeah, it just looks different on my screen, I guess. All right. Well, I was gonna. Yeah, you just uploaded that. Darn.
I just dragged it to the chat part.
And that
where
works.
Yeah,
Right.
I was just trying to see if it worked, and it just sent.
Okay, let's see. I'll try it. No, it's not. It's really not working. Okay, I'm not crazy. I promise. It's really not working. Okay, so I'll just maybe email it to all you guys separately. It was basically just some Orgo 2 documents for you to kind of just review before you go to Orgo 2. But okay, I can get that to you guys another day. Alrighty. Okay, so we're just gonna start over here. So again, reaction, I guess, I don't know where we left off, so we'll start with reaction 1 or something like that. And this is gonna start at chapter 8 material, so we're gonna really pick up on the radical stuff and then kind of just keep going from there. Okay, so really the first reaction, I guess I will call it, is free radical bromination. Okay, so free radical bromination. Okay, and we're just gonna do an example. So an example of that would be like, let's just take, we like this typical example of this, this isomer butane, and essentially you're going to treat it with Br2, okay? And I'm just gonna write H nu or delta, okay? So remember, it was light or heat. Those were the two propagating sources. And remember that we get the addition of the bromine at the more substituted position, okay? So this is the major product, so I can say maybe major, okay? And then we get maybe a little bit of minor. So any of those minors could be at the other position, so minor. Okay, so basically, is this stereospecific or regioselective? No for the stereospecific. So stereospecific question mark, no. Regioselective question mark, yes, it's definitely regioselective because you have basically, addition to the more stable position. Okay, and then in terms of mechanism, I guess I should have done the mechanism before. I kind of forget our formatting. But remember, we had 3 distinct steps. So in the initiation step, okay, now I guess I should have made this nicer. Initiation, but essentially it's BR. We had this, some sort of heat source, and it did this homolytic cleavage. Remember, we had these fishhook arrows, okay? So it basically shows that we're gonna get 2, equivalents of, bromine radical. And then, we're gonna go to propagation, okay? So propagation are the next steps. So again, there's at least two steps in our propagation. So we're going to take, our carbon hydrogen bond that is going to be, proton abstraction. And we're going to take, a new equivalent of bromine, diatomic bromine. Oh, I'm sorry, not yet. Okay, so the first step is this bromine radical that we had, from in the initiation step, going to proton abstract one of the, should have done that in red, okay? One of the electrons from this carbon hydrogen bond. Okay, so that's the proton abstraction step. So that's generating, this tertiary radical, okay? And then HBr is a byproduct. So maybe you'll just write that was proton abstraction. That's kind of the main key here, proton abstraction, okay? So that was the first step of propagation. And then we can have one more propagation step where we take that main radical that we generated, and then this was where we had that second, equivalent of bromine, or excess bromine hanging out. And then that bond is going to be broken, okay, to generate that plus the bromine radical again. So that was the end of propagation. And then in termination, I just always show the easiest one and the 2 bromines coming together. Okay. So again, this one was the weird multi-4-step mechanism, okay? So if you want to make it nicer, basically you could just, write this all out and then put the 2 questions, regioselective and stereochemistry at the bottom. Sorry, kind of forget how we formatted it. Okay, so is everybody good on free radical bromination? Good. Great. Okay, so the next thing, so reaction 2. So reaction 2 is free radical chlorination. So free radical chlorination. Okay, and remember, this one was basically the same thing. So I'm not going to draw out the full mechanism again, but basically let's take that same starting material. Okay, let's treat it with chlorine gas instead of, bromine, and H nu or heat. And basically you can get 2 types of products. You can get this one, and you can also get, this one. And, we said that actually these were all kind of major products. So I'm going to write major and maybe capital major, just to realize that both of these are actually considered major. And the reason that is we said that this was, not really regioselective. This was not a regioselective reaction because, the chlorine radical is more reactive or more unstable. Remember all of those things that we talked about. Okay, so in terms of mechanism, I'm just going to say it's the same exact thing, just all of the protons are now susceptible to being removed. Is there stereo specific, things to worry about here? No, not really. And is there regiochemical things to worry about here? Well, no, because there's no, one major product than the other. Okay, so just maybe something that I would add here is just to say that, the bromine radical versus the chlorine radical, we could just say that, this is more unstable, which basically means more reactive, all of these different things. This is more stable and therefore less reactive. So it prefers, the more stable position, all right? So that's kind of just reviewing free radical, bromination and chlorination conditions. Let's kind of just talk about, the next type of reaction we had. So reaction 3. Oops, reaction, can you see this? Yeah, reaction 3. And that was hydrohalogenation of alkenes, but now in the presence of a peroxide. So remember, it's hydrohalogenation of alkenes, but with peroxide. So I'm going to write ROOR. That's kind of like the abbreviated version of peroxide. So hydrohalogenation of alkenes, but now in the presence of, some sort of peroxide. Okay, and remember, this was actually a regiospecific reaction where we got anti-Markov-Nikov addition of that halide. So remember, in typical hydrohalogenation, let me just kind of bring us back for a second. In typical hydrohalogenation, you typically just treat it with a hydrohalogen like HBr. And then what happens is you're going to get a secondary carbocation, and then that bromine adds to the more substituted position, and that follows Markov-Nikov's rule. In this situation, we're actually going to get not that. So if we do HBr now in the presence of a peroxide and heat, you actually are going to get that product, okay? So it's just a way of moving the bromine positions around, okay? So just keep that in mind. That's very important, okay? So an example of this would be, maybe let's take this example. Let's treat it with, let's do HBr. So HBr, let's treat it maybe with heat, and let me just do the classic example, toot. Okay, so ditert-butyl peroxide. Okay, so again, I'm just going to draw the mechanism below here. So in the initiation step, really what happens is now we're going to have two different things. So before, in our initiation step, we only had one step, okay? It's just the bromine being homolytically cleaved. But now we actually have two distinct steps. So what's going to first happen is the ditert-butyl peroxide is the weakest bond. So the heat there is going to homolytically cleave that into two tert-butyl radicals, okay? Terbutoxide radicals, okay? So we got two of those, two equivalents. And then one of those radicals is going to react with HBr, okay, to generate the bromine radical. So that's why there I said there were two steps instead of just one. So that would be this proton abstraction, okay, and you form a bromine radical. So this was, in a way, proton abstraction. Okay, and you generated, tert-butanol, just a plain alcohol, and then the bromine radical, okay? So that's the two initiation steps. Then in propagation, this is the key step of why we get anti-addition, propagation, okay? So you take your alkene, right? You take your alkene, and you take your bromine radical. And what happens is that this bond, this pi bond, is going to homolytically break such that wherever, that radical is going to land is going to be on the more substituted position, okay? So out of this choice, this tertiary and this secondary, Stephen, there's something in the waiting room? Oh, someone in the waiting room. Oh, okay, let's see. Thanks, I didn't see that. Okay, appreciate it. Cool. So now out of these two positions, out of this, tertiary position or the secondary position, the radical is going to form on the tertiary position. And we said, radical stability parallels carbocation stability. So again, that's something just to remember that when we're ranking these radicals, we're going to be also be thinking about carbocations essentially. So you get this tertiary radical, and then you form this carbon-bromine bond on the less substituted side, okay? That's why, you know, this this anti-Markovnikov addition is happening. Okay, so that's the propagation step. And then in termination, basically, what you're going to have is just a proton come by. So where's all this? Actually, you can show the second propagation step. I forgot to show the second one real quick. And that would just be, remember, always assuming that excess reagent is there. And this is going to do another proton abstraction to kind of like get rid of that radical. Okay. So we get, you know, you always have to show synthesis of that full, you know, haloalkane. So that's, you know, the main product. And then that last termination step, I know I'm running out of space. That last termination is just, you know, maybe I can just show maybe that plus that. And then the two of these kind of coming together. Okay, so that's nice. And then you get two, and then you get, oh, not two, I'm sorry, you get just one molecule of that. Okay, so that's kind of really what we want to talk about there. And then in terms of stereochemistry, no. In terms of regiochemistry, yes, but just remember this is anti-Markovnikov. You know, Markovnikov, whatever. Okay, so something like that. Anti-Markovnikov. Okay, so that's reaction 3. And again, you know, this bromine, I should just maybe indicate that there's chirality there. We go through, radicals are just like carbocations, they're sp2. Yes, you would have a racemic product here. Sorry, just drinking my coffee. Okay, so yeah, definitely would be racemic there. So remember, those are sp2 centers. We have that p orbital. You can attack from the front or the back. Okay, so reaction 4. So I think this is the last radical reaction we had. So it's allylic bromination. Okay, so just remember the key things we had to remember here. Allylic bromination. Okay, so we had that N-bromosuccinimide reagent. I'm just going to draw that. I know that Lewis structure is kind of important. So it comes from succinic acid, so 4-carbon dicarboxylic acid, and then we have the cyclic amide version, and then it's this, you know, homolytically liable N-bromine bond. So that's kind of like the main bond that we have there. That's weak. So that's NBS. I would just write that. Okay, so let's kind of show an example of, you know, of this. So example could possibly be, let's do that, and let's treat this with NBS and heat. Okay, you know, again, heat or light, whatever you prefer. Okay, and remember, we don't really know the full mechanism, but we do know that we're going to go through this main radical. Okay, so it's going to be the allylic radical. And out of what is the allylic position? Well, the allylic position is the 1 carbon adjacent or 1 carbon removed from the alkene. Okay, so this is the allylic radical. And something we always had to check for was for possible resonance with that radical to see if the alkene can become a more stable alkene. Okay, so basically, let me just show the potential resonance here. Okay. And you can get this other structure. Okay, so now when you're comparing the left and the right, you see that you have this, you know, mono-substituted alkene, but a tertiary radical. And then here you have this tri-substitute alkene and a primary radical. So which one wins? Does the better radical win or does the better alkene win? And we said that it's the better alkene that wins, okay? Because alkene stability far outweighs, in terms of thermodynamics, radical stability. So we like this radical better. So always check for resonance. And then now that last step was just the bromine adding on to that position. So from there, you just get this nice bromine adding there. Okay, so that's your main product. So was this stereo-specific? Definitely not. Was this regio-specific? Yeah. This is tough. I don't really know if I should classify this as regio-specific. I'm going to say yes, just for now, because you do have to. You definitely have to think about, you know, the region of this pi bond. We are thinking about the more and less substituted versions. So I'm going to go ahead and call this regio-specific. I don't think you would ever be asked that on the final. Okay, but there you go. So always just remember, maybe I'd write a little note to myself: check for resonance with intermediate. Check for resonance. That's kind of the key here with intermediate. And also note that, you know, alkene stability always wins. Okay, and that's the end of chapter 8. Okay, so does anybody have any questions about chapter 8 reactions? I think we're kind of good on remembering all those things. Okay, so I'm not gonna go in, like, it's weird for me to draw boxes of SN1, SN2, E1, E2. I mean, I guess I could, so I'm actually gonna just flip it on the other page. So you can keep going if you guys have room, but I'm just gonna do it on the back. So we have 4 reactions to cover, I guess, SN1, SN2, E1, E2. Let me just do that on the back. Okay, so I wasn't gonna do them, but I guess I could. Reaction 5, okay? And we're gonna do just nucleophilic substitution, nucleophilic substitution. And I'm gonna write unimolecular. Actually, not yet. I'm gonna write nucleophilic substitution plus beta elimination. And I'm just gonna write in parentheses unimolecular. Okay, so that's kind of indicating, and maybe you can also put maybe in parentheses SN1, and this is E1, okay? So this is reaction 5, nucleophilic substitution and beta elimination. Specifically, we're talking about the unimolecular versions, and this is the SN1, E1 pathways, okay? Let's just draw an example of that. So we know for sure, let's do the starting material where we know for sure we're always going to go through this pathway, and that's going to be probably a tertiary starting material. So I'm thinking, you know, maybe something like this. So I'm just going to write in parentheses tertiary, just to remember that it has to be kind of this, this situation. And remember, the rate determining step was dependent on, you know, that leaving group leaving, okay? We couldn't have any nucleophile attack because of sterics. So our rate determining step, I'll rate that RDS, is dependent on that leaving group leaving by itself. And we always generate, we go through this carbocation intermediate. That's also something that you guys should know. SN1 and E1 always goes through a carbocation intermediate. And then now if I want to go through the SN1 pathway, we can say, let's just treat it with a weak nucleophile, weak base. I'll rate that. So I'm just going to rate WN/WB, so you guys recognize that's a weak nucleophile, weak base. That promotes, you know, this SN1, E1 pathway. And also just keep in mind that this is a protic solvent as well. You can kind of imagine that as protic. I'm just going to rate protic. Okay, so the SN1 products are going to be, you know, that. Okay, and we're not chiral in this situation, but we typically could get racemization. Just keep in mind, I'll put ... Racemization is always possible here. So we get that racemic mixture. And then if you wanted to go to the E1 product, there's a couple of different beta positions here, beta 1, beta 2, beta 3, all equivalent. So, you know, in terms of this situation, we don't have to think about, you know, the Hoffman or the Zaitsev product. We're really all going to get the same thing. So really, you can just imagine, you know, this beta. So I guess let me show addition. So you could attack into there, or in this situation with the CH3OH, I just want to show maybe in another color. That the methanol removes a proton from the beta position, donates that electron density in to form that, and then we're going to get this alkene, okay? So I just also, again, I'm going to put a note to just remember Hoffman versus Zaitsev. Okay, and I'll put underline Zaitsev, okay? So that's kind of all we want to remember with SN1 and E1 is that we're really limited to these bulky starting materials, so tertiary and secondary. So I could also say, you know, and some secondaries, just so we remember that. Okay, the rate determining step is dependent on that leaving group leaving. We form a carbocation, and then from there you have 2 different things that could happen. You could either have substitution at that position because it's a weak nucleophile, or you could have the basic version where the nucleophile doesn't act as a nucleophile, but instead of base, removes that proton and donates electron density in. We always are regioselective in that case, where we do want to form the more stable alkene. So in terms of that, regiospecific, yes. Stereospecific, no, because we get racemization. There is no one enantiomer over the other. It's definitely regiospecific though in terms of alkene stability. Okay, and that's that for reaction 5. So let's do reaction 6. So I guess reaction 6 I'm just going to do is nucleophilic substitution. And that we are just going to call bimolecular, because this one is just going to be bimolecular. And this one I'll also just say is SN2. Okay, so now reaction 6 is just SN2. Are you guys liking this so far? Am I boring you? I don't really know because no one's saying anything. Good. All right. Awesome. Good. Happy that you guys are happy. Okay. So nucleophilic substitution. So now we have to remember what our starting material was. It wasn't, this tertiary starting material for sure. It was definitely either a primary or a secondary. Remember, secondary is that gray area. So let's do, maybe I'm keeping it really simple on this just because, I want you guys to, have the space and whatnot. But, the rate determining step is interesting now. It's bimolecular. Actually, let's go back to this. I just want to add one more thing here. So the rate law was kind of something important. So the rate is dependent on some sort of constant K, and then it's just the starting material. Okay, so I'm just going to write in brackets, it was that, and it was unimolecular. I think that's definitely worth noting because these rate laws kind of get talked about sometimes. I wouldn't be surprised if she has you, pick the rate law. Okay, so that's the rate law. Okay, and then here, so the rate determining step is going to be dependent on, the nucleophile being present. So what do I need here? Well, I'm going to have a strong nucleophile. And we said those would be, something like Na, N3. Okay, so how did I know that? Well, once I dissociated that spectator ion, we said strong nucleophiles are things with, negative charges. We said those charges make them strong. So this would basically be equivalent to saying strong nucleophile. So instead of weak nucleophile, we have a strong nucleophile. Instead of a weak base, we can also say that we have a relatively strong base, because another thing I want to write is that nucleophilicity, that's something to always keep in mind. Philicity always parallels basicity. So again, in those ranking things, if we're saying rank the following molecules in terms of their increasing nucleophilicity, you can use your base rules if you want to. If they say the base rules, if they say ranking in terms of increasing basicity, you can kind of think about them as nucleophiles. Basically, how branched are they? How heavy are they? So you can just kind of use that logic again in your ranking problems. Okay, and then another thing that we had here was some sort of aprotic solvent. So I'm just going to write aprotic solvent because there's a lot of those. And then maybe in parentheses, I'm just going to keep in mind DMSO, just so you guys can remember that. And the rate determining step here is actually dependent, and I'll put RDS. The rate determining step is dependent on, the azide being present. So it's going to attack, okay? And that's what's going to facilitate the removal of the leaving group. So before, it was just the leaving group leaving. Now you can see we have two arrows. So what happens is you would typically have inversion of configuration. I know this isn't chiral, but I'm definitely going to write that. So just ... inversion of configuration for sure. So I'm going to say that would be like R to S or S to R, something to note. And you go through, just remember in this transition state, so here, let me just kind of draw a different scheme of that. You go through this, I'm just going to draw this example. Okay, so this is kind of my transition state. Okay, so you see that negative nucleophile is coming in, okay? And that's going to facilitate the removal of the leaving group. So just keep in mind, this was called the trigonal bipyramidal transition state. Okay, how did they get that name? Well, look, this looks like a triangle in the center, okay? This three-pointed vertice, whatever thing. And then bipyramidal, well, two pyramids. So if you just kind of look at that, that looks like one pyramid, a triangular base and a point. And then here, triangular base and a point. So trigonal bipyramidal. All right, so this would be kind of the summary of SN1E1 and SN2, okay? So that's kind of obvious. When we didn't have these conditions, then we would always have to think about the SN2 product, the E2 product. And that's when it got kind of tricky. I think we have a question in the chat box. What do we have here? Abby, also, do you think it'll be more, oh, Leah, what is the average on the final usually? Honestly, Leah, I don't know, because the final was recently introduced into the class. I think it's only 2 semesters old. So I don't really have a great average for you based on that. Typically, I think it was higher than exam 3 and 4. I think it's like in the 70s, high 70s, like not like abysmal, pretty decent. Okay. Also, you think it'll be more general servant, vice versa? I think you guys, if there's anything to study, it's all your reactions. Like I would definitely go through your reactions, because in doing that, you kind of know what stereochemistry you need. Like you kind of already do that in all your reactions. So I would just do that. Brian, for S1E1, we put also, oh yeah, we should probably put that. That's great. Thanks, Brian. So everybody, we're just gonna go back to reaction 5 real quick. And I think that's great. Let's just check for rearrangements. Okay, that's kind of another key thing. Key arrangements. And how do I know that? Well, let me kind of just draw an arrow to this carbocation, okay? I kind of like these short boxes. They kind of just bring everything to the front of your brain. Just look real quick. All right, great. Okay, so then we're gonna do reaction 7, and that's probably E2. Reaction 7, so that's gonna be beta elimination. Okay, and that's gonna be E2. Okay, let's just do an example of that. Oh, I didn't really rate bimolecular. I should rate bimolecular. Okay, so I want to get a good example for you guys. I kind of wanted to do both examples of, like we had in competition with the SN2, and then we had in competition with the SN1, but let's see if I can find those again. Okay, so let's just take like this example. We had this, let's just do the example. And we had, let's just do this, and let's just do that, and let's treat it with, I don't know, maybe NaOCH3, and then CH3OH. So remember, we said anytime we had these oxygen, based nucleophiles, it was kind of like a good hint that those were going to cause the E2 pathway. And we rationalized that there was some sort of pKa value threshold. I believe it was 14 or something was the cutoff. And these, groups or these reagents fall within that category to make them sufficiently basic and therefore not that great at nucleophilic addition. Okay, so they prefer the proton not to add into a carbocation. And how did I do that? Well, basically, instead of making this, if I had a polar aprotic solvent here, like DMF, acetonitrile, DMSO, any of those, this would be a relatively good nucleophile and a relatively good base. But by introducing this polar aprotic solvent here, we kind of decrease that nucleophilicity, but still maintain the basic properties of the reagent. So what happens here is that we're going to actually have, an alkene form, and it's bimolecular. So how does that work? Well, we need kind of this proton to be in what we call the anti-coplanar configuration. So I'm definitely going to draw a Newman. I think that was kind of the key with these reactions, is to remember to draw your Newman projections or chair conformers. So the Newman is going to look like this. So it's hydrogen, H3C, and then also CH3. And then on the back carbon, it's going to be bromine, proton, CH3. So with respect to the leaving group and the proton that has to be removed, we already achieved this anti-coplanar configuration. Okay, so anti-coplanar, that's definitely something to keep in mind. And we don't have to rotate in this situation, but you can imagine that the lone pairs of that methoxy group is going to deprotonate the proton. You're in the right orbital configuration already to donate that in and facilitate the removal of the bromine. So how do I know which alkene to draw? Well, if we didn't have to do any rotating and it was already in kind of this trans framework, you can leave it in the trans framework. So that's going to be, something that looks like that. Okay, so this would be the E alkene. Actually, you don't actually have any stereochemistry to consider here because these are both methyl groups, but essentially you could just leave it like this. So you just have to remember the anti-coplanar configuration, and typically we're going to get Zaitsev if we can, so let's write that. We would typically want Zaitsev if we can, except with the bulky bases, okay? And that's definitely right what those bulky bases are. So that's LDA, or we had, this example. Okay, so those two, those terbutanol or LDA, those are our bulky bases, and those gave us Hoffman always, okay? Hoffman, so the less substituted. So just think about those things, all right? So you had E2 was kind of always in competition with everything. So it was always like SN1 and E1 were always in tandem. Remember, SN2 was like by itself in the opposite spectrum of SN1E1. And then, E2 could arise in, either this one, or this one, just depending on like what we were given, okay? And that's it. So that's kind of a good review of all that old stuff. Let's talk about chapter 10, okay? So that's pretty good. So we're gonna be on reaction 8 now. Reaction 8, okay? And I think the first one, let me remember, I think it was, yeah, so Alkoxide anion synthesis, let's call it that. Okay, Alkoxide anion synthesis. Right. So clearly, let's do an example. You start with this main alcohol reagent, you treat it, and there's two different things. So we can do either sodium hydride, my personal favorite, or you can do 2 equivalents of, pure sodium or 2 equivalents of pure lithium. Again, either of these would work. And I'm just going to draw the mechanism. So we have the source of hydride, okay? That is going to remove the proton and kind of just generate that alkoxide anion. We just want to keep in mind that this is a relatively strong nucleophile, strong base, typically used in what we called Williamson ether synthesis. I think that's a common name of one of the reactions they like to teach. Okay, so it's just a way that we can make this reagent. That's a good nucleophile. We could do that under aprotic conditions like DMSO. We could also use it to eliminate if we did it under protic conditions like ethanol. Okay, so that was basically the way to do that. And there was nothing really more to cover. Okay, so that was nice. Then the next reaction, reaction 9. Oh, I actually didn't say anything here. Actually, let's go back to reaction 6 real quick in terms of regiospecific or stereospecific. Regiospecific, yeah, I don't know. This is starting to get confusing. Stereospecific, definitely yes, because we're having the inversion of configuration. Regio, you heard that. Regiospecific, I don't know. I wouldn't really say this is regiospecific because like we are limited to these like primary starting materials, but I wouldn't say that that's a regiospecific argument. Like we're not getting addition at a more or less substituted side. So I'm just gonna say no. Stereospecific, I would say yes. Okay. Again, this is just my personal opinion. I don't really know. Regiospecific versus stereospecific. Regio, I would say yes with respect to the alkene. We try to prefer the Zaitsev unless, we get the Hoffman. And even if it was the Hoffman, it would still be regiospecific. Instead of stereospecific, it's definitely not. Okay, and then here, none of that even applies. Okay, so let's go to reaction 9. Okay, so the next thing is going to be alcohol to haloalkane synthesis. So I am just going to say HX addition to alcohols. Okay, HX addition to alcohols. So an example of that is going to be, let's just take maybe something that looks like this. Okay, take this alcohol and let's treat it with, something like HX. So let's just do HCl. Okay, and remember what happened is we had this protonation step. That was the role of using this acid. Okay, so now we convert this from let's keep that in mind, this was a bad leaving group. So let's just say that this hydroxyl is a bad leaving group. Okay, and we're converting it into this protonated, basically water substituent. And now it's charged. So once it leaves, it will be neutral. So this is a now good leaving group. So remember, the whole concept of this chapter was to make alcohols, which are in general really bad leaving groups. Because why? In the chat box, why are alcohols really bad leaving groups? When they leave, they are, one word I'm looking for. When they leave, they are unstable. That's good, but I'm looking for, it starts with a C. They are charged. Negative works too. They're charged. Okay, so that's the point. Is water when it leaves is neutral. When hydroxide leaves, it's a charged negative anion with no resonance possible. So obviously the better leaving group is the neutral species. So after that, you kind of generate some chloride anion. And I use this example on purpose because now we have a little bit of competition. Okay, so we have SN1 possible, but we also have SN2. Okay, so I just want you guys to keep in mind that, with HX addition, you can use it with any alcohol, and you just have to keep in mind that in terms of the major stereoisomers that you're forming, it's dependent on like the substitution of your leaving group. So if this was a tertiary alcohol, you would get only products from the SN1 pathway. secondary, meaning that 50-50 racemic mixture. If it was a primary, you would get, exclusively just one product. You would get exclusively one enantiomer in the SN2 pathway, 100%. But if you have the secondary, you have, I would say 25%, one stereoisomer of the SN1, 25% the other stereoisomer of the SN1, and then you also get 50% of the SN2. So, in terms of major stereoisomers, you would draw them, you would draw the amount, but you're not required to say like percentages, everything like that. So really, in terms of SN1, what do you get? You get that carbocation intermediate, because it leaves on its own, okay? And then you had chloride addition there. And let me just make this a chiral molecule so that we kind of have to see that. So now we can get chloride adding onto the front or the back, and you basically get two major diastereomers of chloride. You get that, and then you also get that. So that's the SN1 products. Okay, and then in terms of the SN2, let's just say that this alcohol was already on a wedge. Okay, let's say this alcohol was already on a wedge. So what's happening is that, since the wedge is already sterically hindered, we could only attack from the back side, that chloride. And if it attacks from the back side, you exclusively only get that dash product. Okay, so notice how you would have probably a greater quantity of these in solution than that one, but essentially you would get the same major stereoisomers. I just wanted to show that you have both routes possible. Okay, and yeah, I think again all the regiochemistry and stereospecificity stuff applies from SN1 and SN2 above, so we don't have to go through that again. Okay, so HX addition to alcohols. Yeah. All right, bye Tisha. I hope you had a great semester. See ya. Good luck on the final. All right, so reaction 10. Reaction 10. Okay, so that's HX addition to alcohols. Again, the whole goal was to make this a good leaving group. So now we're going to just do PBr3. So this is phosphorus tribromide treatment of alcohols. That's really the only way I'm going to call it. Treatment. How do I spell that? Treatment of alcohols. Okay, treatment of alcohols. Okay, so essentially, let's just take a new example. This is again another Lewis structure you need to know. So let's just do that, plain ethanol. And we're going to treat it with PBr3. Okay, so let's just draw that Lewis structure. So it's only 3 bonds to bromine, okay, which basically makes it an electrophile. So this is my electrophile. Okay, so the lone pairs on the oxygen are going to attack the phosphorus, and that's going to remove a bromine. So you actually generate bromide from that step. Okay, so remember what that did was it made this into a very good leaving group. Now it's positively charged. Okay, so that's a good thing. And then that bromide that we generated is going to attack in an SN2 fashion. Remember, the two reactions we're talking about, this one and then reaction 11, are SN2 only. So that was kind of the key there. You were limited, and that's important to write, we are limited to primary and secondary alcohols only. Alcohols only. Okay, that's really important here because that halide only comes back and attacks in an SN2 fashion. So you would typically get an inversion of configuration, but essentially it's that and that. So you get a 2-carbon fragment with a bromine, okay? And your waste product is HOPBr2, okay? So again, I'm just gonna write that. Typically you would get inversion of configuration, right? Again, that makes it stereospecific, this reaction, all right? So yes to stereospecific. Okay. So that's really simple. Just remember that you need to know that. All right. So then the next one. So we're going to use some thionyl chloride treatment of alcohol. So it's just the exact same basic scheme, but now we're going to use a different reagent to generate a chloroalkane instead of a bromoalkane. So reaction 11 is going to be SOCl2 treatment of alcohols. Okay, so let's kind of just take another look at that scheme. So let's just do maybe, I don't know, maybe something like that. Okay, and typically you see this pyridine reagent also paired with it. It just acts as a proton sponge to, change, because you generate hydrochloric acid essentially in this reaction. So I'll just write that down here. Pyridine basically acts as a proton sponge. It basically helps with the pH. So since you're generating so much hydrochloric acid waste product in this, you're really getting into that acidic pH range, and pyridine is a basic molecule which just kind of neutralizes that waste product, so you're not going to degrade your main molecule. Anyway, thionyl chloride's main skeletal structure looks like this. Okay, that's kind of important. So we know that the nucleophile again is going to attack into this electrophilic center. Okay, so I could see Dr. Peterson definitely asking you guys like, a set of nucleophile electrophile questions like, what's, points an arrow to this bond and says, what is this atom, what is this, a nucleophile and an electrophile? And you would say electrophile, because you do know what thionyl chloride is. If Dr. Peterson were to ask, what's the, is this a nucleophile and electrophile for this phosphorus? You'd also say electrophile, So I could definitely see Dr. Peterson, again, same thing here. What do you think the hydride is? Well, the hydride's a nucleophile. So we can, extend all of that, beginning material to now the later reagents. Anyway, what happens here is you don't actually get the chloride forming first. You get kind of this pushing of pi electrons up into the carbonyl. So really that intermediate is pretty crazy looking, but it looks like this. OH, S, O minus, Cl, Cl. Okay, so you have this kind of really big molecule. And what happens is that the O minus kind of resonates back down, and that forces now the chloride out. So you still have this crazy intermediate, but now you finally generated your chloride. OH, S, O, Cl, and now you have chloride. And again, this is going to be SN2. We talked about that, the same SN2 stuff. So since this is a wedge, now we exclusively get 100% of that, 100%. I want to say that, okay? So just a way that we can treat this, with, I'm just gonna write same thing, inversion of configuration. Okay, so notice the mechanisms are pretty similar, but a little bit different at the same time. So like before you generated bromide in the first step, here you kind of have to generate it in like that resonance collapsing step, that kind of rearrangement, okay? And I think the last, okay, so we have a couple more in the alcohol chapter. So reaction 12 is going to be the aryl sulfonate, conversion. So I'm just gonna call that aryl sulfonate conversion. Okay, we don't really know much here. So I'm just gonna basically say this kind of general reaction scheme. So this alcohol, and I'm gonna treat it with something called tosyl chloride. And again, that same pyridine. And again, what tosyl chloride looks like, not that you really needed it, but it was toluene, which is just a benzene with a methyl group. And I'm pretty sure it has this like sulfonate group, tosyl chloride. All right, so that's, I think, the main reagent. Not 100%, but I'm pretty sure. And essentially all you needed to know was that it's going to basically convert this into something called OTS, which is just a good leaving group. So that's just something we should know, that this is a good leaving group. And also something that you should note is that the stereochemistry is retained. This is the only reaction that I know. So stereochemistry is retained. Okay, so if this was R, then this is R. If this was S, then that was S. Okay, so that's kind of just, and that's really all you need to know for that. It was just a way to, make the alcohol a good leaving group directly. We don't know the mechanism, nothing like that. All right, so we're gonna keep moving on. So, okay, I guess I can fit it here. So I'm gonna continue with these boxes, but if you guys have more paper, just, take the time and fold it now, because we're running out of space. Okay, so the next thing is going to be reaction, what number? 13. So reaction 13 is going to be dehydration of alcohols. So dehydration of alcohols. Let me just draw like a line so you guys know that that was the old stuff. Okay. So dehydration of alcohols. Let's just do an example of this. Okay. So let's just take maybe this tertiary alcohol. Let's treat it with sulfuric acid. Heat, and remember, we're going to drive it to completion. This is Le Chatelier's principle. We're going to remove water from the system so that we can drive the completion to the end. This isn't really a favorable reaction, but we can heat it and pull water from it to, force it to go to completion. So what does the role of the acid do? Well, it just protonates that alcohol into a good leaving group. Okay, so essentially you're left with this. And this could happen in an E1 or an E2 fashion. So in this case, it's E1 because, you know, this is a pretty substituted starting material. So I'm just going to say line E1. And what happens is that this water can leave on its own. Again, you go through this carbocation. And the key, again, is going to be to always check for rearrangements, okay? Because that was the key with these, you know, predict the product questions was on the test. What some students kind of got confused was they forgot to do the hydride shifts or the alkyl shifts, and you kind of got a different structural isomer than, you know, the correct answer on the test. So always check for any rearrangements there to make a more stable carbocation. Here we don't. But anyway, the conjugate base of sulfuric acid, which is HSO4 minus, okay, so HSO4 minus now is just going to now basically do an acid-base reaction. Okay, so this is the elimination step. Remove that and put it in. Okay, so we essentially formed, you know, that, an alkene. Okay, so this was a really important reaction because it was a way that we could now do all the chapter 6 and chapter 7 reactions with this alkene, and we're bridging chapter 10. Okay, so you guys should really know this connection, that this reaction bridges the alcohol sets of reactions with the alkene-alkyne reactions. Okay, so this is probably where you're gonna have to definitely use this in your mechanisms on the test. All right, so that's where we are for dehydration of alcohols. So again, check for rearrangements, and again, we prefer the Zaitsev product over the Hoffman. So Zaitsev over Hoffman. Okay, again, that's that. Okay. So reaction 14, okay? So this is going to be weak oxidation of alcohols. Okay, we're almost done. Weak oxidation of alcohols. So an example of that, I'm going to do a couple of examples. So we're going to do basically primary, okay? I want to do secondary, and I want to do tertiary. And we know that our only weak reagent is PCC and DCM. So I'm going to write that for all of these, PCC and DCM, PCC and DCM, okay? And again, remember, I'm going to write this in the bottom, the orgo definition for oxidation. So I was going to write orgo definition of oxidation was the loss of a carbon-hydrogen bond and then the gaining of a carbon-oxygen bond. Okay, that's the new definition that we're going to get used to, okay? So we basically, as a requirement, need one carbon-hydrogen bond, okay? At least one. So let me just draw them in. At least one carbon-hydrogen bond to do this oxidation. So essentially we have this and that. So that's a requirement. And what we do is we stop at aldehydes and or ketones. We don't go to carboxylic acid. So here we have a 2-carbon fragment. So 2-carbon fragment. And we're going to stop at the aldehyde, okay? Same thing here. We have a 2-carbon fragment, but now it's a ketone, okay? And then here we actually have no reaction, okay? Because we don't have that requirement met where we have to have at least one of those protons there, okay? So I think that was good for weak oxidation of alcohols. Just know that primary, let me just actually probably write that down here. Primary alcohols go to aldehydes. Secondary always go to ketones. Tertiaries do not react. Okay, let's go to reaction 15. This is the last one in the chapter, and this is going to be strong oxidation of alcohols. Okay, so essentially what does that look like? Well, we have the 3 examples again. Let's just use the same ones. OH, secondary, tertiary. Let's all do just different reagents. So this one maybe I'll treat with Jones's reagent. This one I'll do Na2Cr2O7. I believe it's sulfuric acid. And then this one I'll just do another example. So any of these reagents all do the same thing. That's why I use different ones just to show you that they all are strong. So anything that has like those metals, like the chromiums and oxygens and Jones's reagent, those are all strong conditions. And we're basically gonna convert all of these to really, really good or really, really strong oxidants, basically carboxylic acid. So that same requirement applies. So here we can do 2 rounds of oxidation. So that's kind of like the goal here. So basically you definitely go here first, okay? And then you go one more step later because there's this extra proton. Okay, so this goes through the second round I'll write that there, second round of oxidation. And you go one extra step further, you remove that last proton, and then you gain another carbon hydroxygen bond. Okay, so you get this carboxylic acid. Okay, so in this one, so again, you only have one proton present, so you can only do one round of oxidation anyway. So you stop still at the ketone. So it's the same exact, kind of let me underline this one. This one is the exact same that you got with the weak condition. Okay, just kind of keep that in mind, that it doesn't matter if it's strong or weak for secondaries because you can only do one possible round anyway. So you're never going to get to the carboxylic acid if you're secondary. And that makes sense. We can't form a carbon. You know what carboxylic acids look like. There's no way to add an extra OH bond there. Okay, and then again, this last example, there are no protons available, so no reaction with tertiaries at all. Okay, and that is a good review for the reactions of chapter 8, 9, and 10. Okay, so again, real quickly, I'm just going to cover those quick chapter 11 ones. So reaction 16 is going to be epoxide synthesis. And I'm going to write in parentheses, I'm going to do the peroxide route. This one was really nice. So we just took, that plain alkene. We subjected it to MCPBA in this DCM solvent. And we know we went straight to that epoxide and no mechanism required. And this was, okay. Was this regio-specific? No. Was it stereospecific? No. So really all you have to know is that, okay? And no mechanism required, okay? Just know that you can approach from the top or the bottom face of that pi bond. There you go, all right? That was reaction 16. I have my paper now. Right? I know. Thank you guys for bearing with me. Okay, so now we're on which reaction? We're on reaction 17. Okay, so reaction 17 was again epoxide synthesis, but this time it was via halohydrin. So halohydrin route. Okay, so this was kind of a review reaction. So what we did was I'm just trying to pull up this stuff. Okay, so what we did was we could take this example of a benzene. Okay, and we had, this vinyl. So this is really just styrene. Okay, this was, remember, that styrene monomer. And basically, the first thing we can do is do a halohydrin reaction. So remember that all the things from that old chapter 6 stuff, where we're going to go through that cyclic chloronium bridged intermediate. So there's a wedge version and dash version, and then water is going to be regioselective and attack into the more substituted position. So the two main things would be hydroxyl chloride, and then you also get this as well. Okay, so then the next step would be to do that intramolecular rearrangement. So treating it with some sort of base like sodium hydride, what it actually does is it removes this proton. Okay, so I'm just going to show this with one example, not both isomers, but essentially you get this alkoxide anion, and due to the dipole moment of the chlorine, we can kind of bend over and fix that deficiency. So the negative actually hits that carbon and closes that leaving group. So this was another way for you to generate that and then plus the other. Okay, so halohydrin route. Again, it was regio-specific and stereo-specific in terms of the halohydrin stuff. That's anti-addition, and water's adding on the more substituted side. But in terms of the second step with the base, we're not having anything there in terms of regiochemistry or stereochemistry. All right. So then there's two last reactions, just how to open those. So reaction 18 was epoxide opening. And we're going to say acid catalyzed. Okay, so an example of that would just be to take maybe, let's choose that same example. Let's just do step 1, MCPBA, and then DCM. And then in step 2, let's just do like H2O and HCl. Okay, so what happens now in this case is you go right to the epoxide. So we know the product of step 1 is definitely going to be, this racemic mixture of epoxides plus other, and that's the product of step 1. And then in step 2, what happens is you actually have hydronium, and I'm not going to show, I think you guys know how hydronium forms at this point. And, we activate, this is ring activation. I keep calling that name. It's ring activation. So let's kind of say that. This is ring activation. Okay, so you protonate it, and it makes the what? And it makes the electrophile more electrophilic. So essentially what you get here is this kind of protonated electrophile, and then now water is going to be regiospecific and attack the more substituted side for reasons we've proved. Those were the resonance structures. So if this is a wedge, then the hydroxyl group came in from the back. So really the product should have been dashed hydroxyl, okay, and then you have this other hydroxyl, and then you also have the other plus other, the wedge version, okay? So you get this diol. What a diol is, 1,2 alcohol. Okay, so 1,2 alcohol. All right, so yes, this was regiospecific. Yes, for the more substituted side. Let's just say that. Yes, more substituted side. Okay, those were all the things we had talked about. And then the last reaction of organic 1, you guys finally made it. Reaction 19, epoxide opening under basic conditions. Or basic catalyzed, whatever you want to call it. Okay, so again, the same exact example. So I'm actually going to go straight to the product in this situation. So let's just go with this one main structure, and we're going to treat that with maybe step 1, NaSCH3, and then step 2, maybe H+. Okay, so the difference between the first one and the second one was, we didn't necessarily need the NCPBA, but everything was in one step when we opened. Here, 2 things have to happen, so it's 2 steps. So what this is this is a base, so it's going to be governed by SN2, base, sterics, all of these things that we're used to, sterics, bases, SN2, and it's going to attack the less substituted side. So in terms of regiochemistry, yes, and it's also going to be less substituted addition. Okay, so you can imagine that the thiol bond, whatever, is going to come into here. Keep in mind, we have tricked students before. I guess it's not really a trick, it's kind of fair, but you generate the alkoxide first, okay? So just keep in mind that this could be a product that you need to show, like if there's no protonation step. And then that second, proton source is just going to synthesize, that alcohol from there. All right, and that is organic 1, right? So that was a lot to digest. So that's pretty much everything. I don't want to bore you guys, so I think we might just cut it short. But Avery, what are you saying? I don't know what the pinnacle rearrangement is. Does somebody want to share their screen or something and show me what that is? And I can kind of look what that is. I don't know. Anybody? Sabrina, do you want to share? Anybody? Okay. Does anybody have any other outstanding questions? So that's pretty much all I wanted to do. I really just wanted to go over the reactions and do those beginning warm-up problems. Everything else, I guess you should be fine. But let's see. Okay, Robert, I think that's some study stuff. Probably not the final. Can you show your entire paper? Yes. Yeah, I guess Pinnacle might be new. I really haven't heard of it. So this is the entire paper. Hopefully you guys can get it. Okay, so it was only about 5 minutes. It was on exam 4. Okay, does anybody else have any other questions other than that? It's dehydration of alcohols when there's more than one alcohol present. Interesting. I've never heard of that. All right. Well, if there are no more questions about content, thank you guys for a great semester. Stay tuned for some Orgo 2 announcements. Like, I'm still debating what I'm gonna do, like with all my resources and stuff. So I definitely will be giving to you. I just don't know in like what capacity and what context, but that will be coming soon. And keep practicing. And I'm still available through email. And good luck with your future. Don't cry. Don't cry. I'm not crying. You're crying. Love you guys. Good luck. See ya.